So let's proceed for the sample problems presented on the Tomasi book. So first problem, determine the 12-bit linear code, the 8-bit compressed code, the 12 or the decoded 12-bit code, the quantization error for a resolution of 0.01 volts, and analog sample voltage of, say, for example, 0.053 volts value. So for us to quantize this value first, we have to divide our sample voltage by its resolution. Again, we are answering in letter A. Divide the sampled voltage by its resolution. So 0.053 volts divided by 0.01 volts, that would be 5.3 volts. Next, we have to quantize it. So quantizing is the rounding off of that sampled voltage so that we would not be dealing with decimals. So 5.3 volts would be rounded off to positive 5 volts. Now let's encode it into the binary codes with a 12-bit as a 12-bit linear code. So since this is a positive value, we have to put 1 as its sign bit, since positive 1 or positive in binary code as a sign bit is 1. Then, since 5 is as an 11-bit magnitude is expressed in this as 101. So you already know how to convert that from decimal to binary code based on our discussion on the logic circuit. So I would not further discuss that one. Then, if we have now the 12-bit linear code or 12-bit signed magnitude, we have to, for us to easily answer it, I have presented it by parts in here, the 12-bit code. And since we are also asked for the quantization error is because of rounding off, we simply have to subtract our sampled voltage, which is 5.3 volts, by positive 5 volts, which is 0.3 volts. Then multiply it by the quantization, multiply it by its resolution. So that would be the equivalent voltage is 0.003 volts. So that is the quantization error that occurs because of rounding off. Then, since we are asked to identify its 8-bit compressed code, so again, in expressing it in 8-bit compressed code, copy the sign bit, 1, then count the number of trailing zeros. That is 1, 2, 3, 4, 5, 6, 7, 8. So take note, in this example, based on the steps I have presented, the number of trailing zeros must not exceed to 7. So we have only to consider 7 trailing zeros. So 7 trailing zeros, 7 minus 7 equals to 0. Then this 0, we have to convert it into a 3-bit binary code. That would be 0, 0, 0. We have 4 bits, and the 4 least significant bits would be our quantization interval. Since we have automatically 4 remaining bits here, this would be automatically our quantization interval. So that would be 0, 1, 0, 1. So that would be our 8-bit compressed code. 100000101. Next, after getting the 8-bit compressed code, we are asked to decode that into a 12-bit code. So from this, we have to return it into its 12-bit code. So copy the sign bit, even compression or expansion, always copy the sign bit. Next, since we are dealing with expansion, 7 minus this segment 0, that is 7 minus 0, that is still 7. So 7 minus 0, 7, so we have to add 7 trailing zeros. So again, in expansion, we don't need to convert this number into binary bit code. We just have to add up how many trailing zeros. 2, 4, 6, and 7. Next, we have to count how many bits we have already for us to complete this 12-bit code. So this would be 2, 4, 6, 8. Since only 4 remaining bits are necessary, so we don't need to add up 1 anymore since we have the quantization interval here as a 4-bit code already. So this would complete now our 12-bit code. So that's it. We have the recovered code based on our answer. Next is its recovered voltage. Based on this code, we have to decode it as a decimal value, positive, since we have assigned bit as 1, so that is positive value. Then we have 101, so that is equal to 5 volts, or that is equal to 5. Multiply it by its resolution, so we have an answer of positive 5 volts. So let me emphasize that our recovered voltage here, which is positive 5 volts, reflects our quantized voltage here, which is also positive 5 volts. As you could observe, there is actually no compression error that happens. That means whatever value is encoded, it is reflected as is on its decoder. Because it belongs in segment 0, that is why there is no compression error. Next, what if we have a sampled voltage of negative 0.318 volts and the resolution is still the same, 0.01 volts, which is a positive? Then, to convert it into a 12-bit linear code, we have to divide again the sampled voltage to its resolution. Negative 0.318 volts divided by 0.01 volts, that is negative 31.8. And we have to quantize it or round it off. So rounding it off, we have negative 32. Then express it as a binary or 12-bit binary code. So since we have negative here, we have assigned bit as 0. Then 32 is 1, 0, 0, 0, 0, 0. So that would be the binary code of negative 32. And we have the quantization error, sampled voltage minus the rounded off voltage or the quantized voltage. We have 0.2. Then multiply it by its resolution, 0.01 volts. We have the quantization error of 0.02 volts. Next is the 8-bit compressed code. So for the 8-bit compressed code, we have copy the sign bit here, then count the number of trailing zeros, before the first occurrence of 1, that is 5. 7 minus 5, that is 2. So 7 minus 2, 7 minus 5, that is 2. Then this 2 would be converted to a 3-bit binary code. So that is 0, 1, 0. Then we have the first occurrence of 1. We have to drop it or just assume that we have 1. Then the next 4 bits would be immediately our quantization interval, which is 4 zeros. Then our 1 here would be truncated. So we have now the compressed code 01000000. Next is we have to recover the 12-bit code. So copy the sign bit. Next, this segment identifier, subtract it from 7. Since this is equal to 2, 7 minus 2, that is 5. So we have to add up 5 trailing zeros. Then reinsert 1. That is after the trailing zeros and quantization interval. Then copy as is the quantization interval. And reinsert 1 for the truncated bits as the most significant of it. So we have the 12-bit recovered code, and the recovered voltage would be, we just have to decode this value. Since it is 0, that means it is negative. Then we have these values here. This is 32, then plus 1, so that is negative 33 times its resolution. So we have the recovered voltage negative 0.33 volts. Negative 0.33 volts, as you could observe, it is not the same with our original value. So there is a quantization error. At the same time, there is a compression error. Quantization error is when we round off, and compression error is as we encode it and decoded that voltage. Next, letter C. Say for example, we have 10.234 volts and resolution still 0.01 volts. Expressing it in 12-bit linear code. Divide it by its resolution. So we have positive 123.4 volts, then round it off. So we have positive 1023. Then express it, convert it into a 12-bit or 12-bit signed magnitude. We have these binary numbers. Then if we convert it into an 8-bit code, we have 1, copy 1 again, sign bit. Then since we have 1, 0 only here, so that means 7, 7 minus 1, that is 6. So 6 expressed as a binary bit, that is 110. Then the first occurrence of 1, drop it or assume we have 1. Then the 4 next bits would be the quantization interval, so copy it as is. So we have 2, 4, 6, 8. So we have now our 8-bit compressed code here. So the quantization error again is just the difference between the sampled voltage and quantized voltage multiplied by its resolution. So we have 0.004 volts. And we have the 12-bit recovered voltage. Copy the sign bit. Then this binary bit here, we have to subtract it from 7 since this is equal to 6. we have to subtract 7 minus 6, that is equal to 1. So we just have to add 1, 0. Then, after the trailing zeros, we have to add 1 before the quantization interval. After the reinserting 1, we have to copy the quantization interval. And since we have 2, 4, 6, 7 bits, to complete this 12-bit code, we have to add 5 bits. And this 5 bits is our truncated bits. And again, the most significant bits that would be reinserted as 1, and the rest of the bits, or the least significant bits of the truncated part, would be zeros. So we have the recovered code with this. And our recovered voltage would be only to decode this value. Our recovered voltage, again, correction, this would be positive since we have 1 as our sign bit. So this positive 1008 volts times 1 or 0.01 volts would be now positive 10.08 volts. So that is our recovered voltage.